Next is the periodic turns. It is a topic that's very important. So there are two factors, which are effective nuclear charge, E and C, and shielding effect. So first, effective nuclear charge shows you how effective the nucleus is at pulling valence electrons. This is lithium. Lithium, it has 3 electrons, 2 in the first energy level and 1 in the second energy level. And effective nuclear charge for lithium would be protons 3. Full energy level has 2 electrons, so you subtract 2 and then it will be plus 1. So lithium has an effective charge of plus 1. It shows how effective nucleus is at pulling the valence electrons, which is over here. And second, shielding effect is when full energy levels block the nucleus from being able to attract the valence electrons. So shielding effect is what the valence electrons experience by the full energy levels near nucleus, which block the pull from nucleus. So inner electrons shield the outer electrons from nucleus. So shielding effect will be larger for the atoms that have more energy levels, because there will be more electrons in the full energy levels that will block the attraction from nucleus to the valence electrons. So first is the atomic radius, and atomic radius decreases across the period. So if you go across the period, atomic radius will decrease because the number of protons will increase and effective nuclear charge will increase. For example, for lithium beryllium, so for lithium has 2 electrons in the first energy level and 1 in the second energy level. And for beryllium, it has 2 in the first energy level and 2 in the second energy level as well. So they would have the same number of electrons, which is 2 in the first or full energy level, and lithium has 1 electron on the outer side and 2 for beryllium. Effective nuclear charge will increase because for lithium, E and C will be number of protons 3 minus number of electrons in full energy levels, which is plus 1. But for beryllium, it will be number of protons 4 minus 2, which would be plus 2. So as you go across the period, E and C will increase, so the attraction of nucleus to valence electrons will increase, and because nucleus is attracting the valence electrons more strongly, the atom will be smaller. Atomic radius will increase down the table because the number of energy level will increase. So hydrogen will have 1 energy level, but lithium will have 2 energy levels. So of course the lithium will be larger than the hydrogen. Next is the ionic radius. And metals become smaller as they lose an entire energy level. So for example, sodium will be bigger than sodium ion because as sodium loses an electron to become a sodium ion, it will lose an entire energy level. And nonmetals become larger as they have more electrons to attract. So as chlorine gains an electron to become a chlorine ion, then it would have more electrons to attract, and the attraction from nucleus to valence electrons will be smaller and the ion will be larger. Next is the ionization energy. It is the energy required to remove an electron from an atom. Ionization energy increases across the period as ETC increases, because it's harder to remove an electron if the nucleus is more effective at pulling the electrons. And it decreases down the table as shielding effect increases. It's because as you go down the periodic table, they will have more energy levels and nucleus will become less effective at attracting the valence electrons. So because the shielding effect increases, valence electrons will be blocked from the nucleus, it will be easier to remove a valence electron. Next is the electron affinity, and it is the energy absorbed or released when an atom takes an electron. So negative energy means energy is released, and it means that atom loves electrons, and it's more stable when electron is added. Positive energy means it needs energy to take electrons, so it's more stable for an atom to not have that electron. This makes sense because positive energy means the energy had to be absorbed for that atom to take in that electron, but negative energy means energy is released instead, so that atom even favored gaining electrons. Electron affinity becomes more negative across the period because as you go across the period, nonmetals have more attraction for electrons because they have more ETC. They have a stronger attraction to electrons, and it becomes less negative down the table. As you go down the table, shielding effects block nucleus from taking electrons, so the nucleus will be less effective at pulling electrons. Lastly, electronegativity is the tendency of an atom to attract an electron. Higher for nonmetals and lower for metals, because nonmetals have larger ETC, so they will be more effective at pulling electrons and they will love electrons. Metals have lower ETC and they tend to lose electrons instead of gaining. So the love for electrons will be higher for nonmetals and lower for metals. It increases across the period and decreases down the table. This topic is the Coulomb's law. It is the magnitudes of electric forces between two charged species. Two charged species can be nucleus and electrons, and also just two polar molecules. This is the formula. You do not have to memorize it. You just have to know that force of attraction increases as charge increases. For example, in MgCl, there will be higher attractions than in NaCl because Mg has a charge of 2+, so it will attract the chlorine ion more strongly than the sodium ion does. And second, force of attraction increases as the distance between the charged species decreases. So, for example, you are comparing lithium and sodium ion, and you see that sodium ion has to be larger than the lithium ion, so there will be a greater distance between sodium and chlorine than the lithium and chlorine because sodium is much larger and it has more energy levels. So the attraction between lithium chlorine will be stronger than the attraction between sodium ion and chlorine ion, and it will be this. Next is the exceptions to periodic trends and ionization energy. It requires less energy to pull the only electron in an orbital than to pull an electron from a full orbital. So you have an example here. Beryllium has the electron configuration of 1s2 and 2s2, and its ionization energy is larger than the ionization energy for boron, which has an electron configuration of 1s2, 2s2, and 2p1. And as we just learned, as you go across the table, ionization energy will have to increase. But in this case, it decreased. And that is because it's easier to pull the only electron in an orbital, which is the electron in 2p orbital, than pulling an electron from the full orbital, because beryllium will be more stable than the boron because boron has just an extra electron in a p orbital alone by itself. So ionization energy of boron will be less than the ionization of beryllium because it's easier to pull the only electron in an orbital. And next, it requires less energy to remove a paired electron than to remove an unpaired electron because electron repulsion acts upon paired electrons. So you have nitrogen here and oxygen here. And you see that there is a paired electron in oxygen, but not in nitrogen. So the ionization energy of nitrogen is larger than the ionization energy for oxygen, which means it's harder to pull an electron from nitrogen than from the oxygen. It's because from this paired electron repulsion acts upon, and they will repel each other. So it will be easier for us to remove this paired electron than to pull this electron alone without any repulsion. And the last topic for today is the successive ionization energies. So as you remove more and more electrons, ionization energy will increase. So ionization energy for the first valence electrons will be less than the ionization for the second valence electron, because as you remove the electrons, there will be less electrons for the nucleus to pull, and it will be harder for us to pull that electron getting even stronger attraction from the nucleus. So the second ionization energy is the energy required to remove the second electron from an atom. And as you can see in the chart, sodium has a much larger second ionization energy than the first ionization energy. Because sodium has one valence electron, after you remove these valence electrons, sodium will just have full energy levels with 4 electrons. Therefore, it will be much harder for us to remove an electron from the full energy level than just the valence electron alone. So the ionization energy increased by a lot. And for magnesium, it has 2 valence electrons. So after you pull these 2 valence electrons, the ionization for the third electrons will be much larger because it will be from the full energy level. And same for aluminum because it has 3 valence electrons. This is the end of the video, and thank you for watching.